Hello, everyone. This is Professor Ma, and this is the introduction to the sections on the graphs of factorable polynomials. Uh, this is an interesting sections because it ties in a bunch of things together. In particular, it ties in the algebra and the pictures that we are about to make. And so the geometry of algebra. So briefly, we have the last two sections. We talk about a function, the graph of the function of the first degree, y equal to mx plus b, and basically they are lines. And then we talk about a graph of second degree, and so something square x plus something times x plus some other numbers. And these are basically parabolas, either pointing out, pointing downwards. And then how do we talk about graphs in a general or in higher degree case? Well, so this is how we do it. In particular, first we talk about the type of graphs that we are going to look at, the type of polynomials we're going to look at. Factorable. What do we mean by factorable? Everybody knows x squared minus 4. These factors is factorable, is plus 2, minus 2. But here, actually, it's a bit more general than that, including these, x squared minus 2. This factor is factorable because this factor into plus root 2, x minus root 2. And where are these two numbers came from? These are the two roots, okay? R1, R2, and these are roots which you put into this formula for x. You're going to wind out to be 0. You can get it from quadratic formula if you want to go a very formal. In general, if you plug in quadratic formulas, like let's just leave the 8 like a simple case. If you plug in quadratic formula and you are able to get two real numbers, okay, quadratic formula, and you get two numbers, like two decimal numbers, and those will be the roots, which I will call R1, R2, then you can put those numbers here, R1 and R2, and what we are saying is, oh, it is factorable. You factor into these two factors. And so these are factorable. What do we mean by factorable? Or what's not factorable? Not factorable is the ones that we are not going to look at. It's like y equal to x squared plus 1. And when we try to use quadratic formula and you wind up with complex numbers, you factor into complex numbers. Okay. And this is what I mean, a not factorable in real numbers. That's what not factorable in reference to in the real numbers. Okay. So we talk about factorables over the real numbers. In particular, it looks like this. So we say formula is factorable, polynomial formula, if I can break up into, okay, if I take this number out in the front and factor out, then this part somehow breaks into a bunch of like x minus a number times x minus a number times x minus a number into individual roots. Okay, this is factorable, and here's demonstrate how it is factored. Of course, made up, so it's doable. First, you pull out the common factor x cubed, then you wind up with this fourth degree, and it turns out to be the square of x squared minus 4. Then you keep breaking up, and you wind up with a factored version completely over the real numbers. of this 7th degree. Okay. This is a factorable polynomial. So if such a case, then it breaks up into the form like, okay, here's a number 2 in the front, you take it out, and it will be some minus some number that it's a root and to raised to a power, like minus 0 raised to a power, x plus 2, minus another root, and here's minus 2 actually is a root, and raised to the second power, and so on, so on. So the top is the form. If you factor it completely, it looks like something at the top. We need to name the parts from the top. Okay. So in particular, the R1, R2, Rk, those will be the roots. When you plug in the formula, you will get 0. Okay? And so here the roots are 0. Underneath minus 2. You put x to be minus 2. That plus 2 is 0. 0 squared. So it's the negative of plus 2 is minus 2. Then the negative of minus 2 is plus 2. So those are the roots you can extract from the factor form, right? What other information you need? What the other information that turns out to be important is the power or the orders. Is what's the power associated with the root? Associated with the root. Associated over here with 0 is a third power, or the order is 3. Associated root minus 2 is the second power. Therefore, its order is 2. Okay, etc., etc. Okay, so 0 has order 3, minus 2, and 2 has order 2. So if, again, the kind of polynomial we're going to look at are these type of polynomials which assume we can factor it, everything's factored, and these are the important information we need to put on our list. And from this list, we're going to make the picture, the graph. Okay. So now let's jump over to the portion of other graphs. Okay. In particular, graph of polynomial functions is an undulating curve, which at 2 ends goes up. We'll talk about that in a second. Okay. In particular, what is not, it is not broken pieces. Okay, and there's no undefined locations. Every x I plug in, I get a numbers that's y, and there's a point I can plot. So the graph must be continuous. It couldn't jump from one point and broken to another positions. Okay? And the second thing is about the curves of a polynomial is that it doesn't have corners. It's smooth. Okay? And we'll bring that in later. Okay. Now, to graph a factorable polynomials or polynomial in general that can be factored completely, and so these are the two things we're going to do. We're going to do something we say we're going to look at a graph globally. It's from top really far away, look top down, see what a graph looks like, and then we're going to zoom in that important portion. What does the zoom in the middle part look like? Okay, to look at what the outside, the global top down, way down top, the versions, and we first start with the graphs of the starts out with the graphs of extra power, okay, to n power. So there are two types, and this x to the even power versus x to the odd power. Okay. And here's what x to the even power. Here's the graph x squared, and here's the graph of x to the fourth. And we plotted graphing calculators. That's what it looks like. And here's x to the 60. I want to point out, in particular, notice at 1, 1, they all go through 1, 1. And this is x squared. Okay. It is the highest one between between 0 up to 1 is x equal to 1. Okay. So in other words, like for instance, if x is 1/2, then x squared is going to be 1/4. Okay. But notice this is actually 4. Okay. And if I take x to the 4th of the number 1/2, and I'm going to get 1/16. And that curve there for the brown one is actually below the black one, which is the square. In other words, in these segments, it's actually between here and here, -1 and 1, the bigger the power, the lower the curve is. Okay? But if I zoom out, once I pass the axis outside in this part, then the situation reversed. Because what? Because the higher the power you raise, if you take the number more than 1, 2, 3, 4, the more power you raise the number, the bigger the number outcome will be. So the bigger the y will be, hence the higher the graph will. And they switch the position of the height at that locations. Okay, and this happens with all the other power type of pictures. Like here is actually negative even power. So in particular, this is a summary for extra even power. It basically points up like that, or they both point down like that. Okay, as opposed to extra R power. With the third power, when x is positive, y is positive. When x is negative, y is negative. Hence, they have this S shape. Fifth power, okay, seventh power. Notice the same thing with the switching of the position between -1 and 1. And here is the summary of what the x to the odd power. In particular, actually, it should be pointed out there's a kind of special case. Actually, the first power, it doesn't flatten out. Actually, the first power is just a straight line. It's actually minus x. So this is a line in y. Actually, the first power 1 is minus x to the first power. Beyond that, they all kind of make this S shapes, one way or the other, for the R power. So these are important templates. Okay, we're going to use these later. This templates has to do with, therefore, when we factor the polynomial, remember we start with polynomial, we factor them and we look at the order, and that tells you what they look like at the location of that root. Okay, so let's continue more about the graph of polynomials, and that is polynomial undulates and they don't have corners. Okay, they don't have. Remember we said before they're not broken, and nor do they have a pinch point like this. Okay. So from this basic assumption, now we're going to look at how we construct a graph of the factorable polynomials. Okay, let's first look at the global that is from top down. So how do we do that? Well, actually, it's quite simple. That is, if I write down a polynomial, okay, expanded, don't factor. Okay, what tells you happened to the polynomial when from the top down? That means when x becomes very, very large, what basically happened to this formula, and the answer turns out to be O. These formula basically look like just the head, the highest degree. Why? Because the lowest degree term really doesn't amount much compared to the highest degree term. Okay, and think about that. And the highest degree terms is 1 degree higher than the next one. So that means it gets to multiply to the x one more time. So as x gets big, a trillion, a billion, trillions, or whatever, a trillion to a trillion to a trillion power, or whatever, as then the comparisons of the lower degree term with the head, the ratio of the result is insignificant. Hence, the plotting, you can ignore them for very, very large x. Okay, so this is basically the assumptions we're making over here. So you can read and kind of think about it and give a brief kind of argument. That means what? Well, that means that, okay, and then if I were to graph this on my graphing, on my tablets, on my graphing calculator, and this is the screen, okay, where? Here. This part is a screen. And the screen only plots what's in the middle. It doesn't plot what's outside because the outside is infinite. Okay, so but basically there are four cases. If the highest degree term is an even degree, and then eventually it will look like the arms of even degree, actually even degree terms. If it's minus even degree, then eventually the graph has to go down on the sides. Okay, and the same thing, if the highest degrees are R degree, then one arm must goes up, the other arm must go down, and then if it goes the other way, then the other one arm goes up that way, the other arm goes the other way. That's outside the screen. That we call the global view. That is whatever if you go way on, you would look on the graph. Oh, I see what it's doing. Okay. Now you're going to zoom back in and say, what's in the middle? In the middle is the local information. That's where you will need to factor the polynomials and look at what locally tells you. Okay? So basically, we can use sign chart, but let's just jump to you can read this particular example that justify that why the information we have used to graph a second degree formulas. Okay, we know it's a parabola, but let me go to the example where we how do we use the information that we begin to construct the when we do the factors. Okay, so we're going to do the mid portions of the polynomial graph, and remember these templates. Okay, if for the even powers, then at the point where this is the point where x equal to 0, it's a root. So this is what x even power and x to the r power look like at 0. Okay. And in particular, and here's what it looks like if I factor my polynomials. What it will look like if I'm at a root that is odd powered, came from an odd order, okay? And if I come at a root, and a picture at a root that has even order, I just like x squared and x minus x squared. Okay. Let me demonstrate what I meant by that. Okay. Suppose I know the roots. Okay, here I have two roots, R1 and R2. Okay, and I know that their order, the order is 2, and at R2 the order is 3. So in other words, this is a even order. Okay, and this is R order. Okay. Graph over there. So I'm going to put this R1, doesn't matter, R1, R2. Okay. Now, let me go back to the graph. Let's say an odd order. What does odd order roots graph look around that point? Odd order roots, okay, at a point, here's a point at 0, okay? In particular, we're not 0. In other words, basically look like that, unless it's y to the x. Y to x then is a straight line, or else it does this. Y to the x is a straight line. X to the third, on odd order, x to the fifth, seventh, they don't go straight. They flattens out and they flatten out, then they flatten, then sharp drops like that. In particular, in our case, it's a third power, therefore it goes from, since sign chart's plus, that means y has to be on top. So the graph must goes like this, and the sign chart on the other side is negative, the graph, therefore y must go downwards. And so it must look like that x cubed. What does x to the even power look like? What x to the even power look like? They were U-shaped or upside down. And since it's both sides are negative, therefore at that location locally, it looks like that. Okay. Again, depends on what is even or odd powers. You draw one of these curve that's locally. That is, if you look at on a microscope, you got to do that at that point. Okay. And turns out from here, we can have the entire picture because the polynomial behave very nicely. From here, we perform connecting these sections. We think of these as real line going up and down, and how do you connect them nice and smooth? And well, and you just basically goes up like that, and this keeps going up, and this keeps going up. Okay. And that's how we will finish. Okay. Assume this is a factorable polynomial graph. Okay. Hence, here's a real problem that with actual location, how we're going to do this. Well, mark the roots down. The root is x equal to 0, and its power is 1. X equal to minus 2. Its power is 2. X equal to 3. Power is 2. Or orders. Okay. Power is order. So, then I can check the sign chart. Okay, I can plug in for those people who forgot how to do sign chart. We can go back and review the sign chart sections and how we obtain the sign chart. And so for the formula, and this is going to be minus, minus, plus, minus. From here on, I can fill in the little local pictures. So this is order 2. Meaning this one is a little parabola, but it seems upside down because it's negative. Here's order 1, and positive on this side, negative on that side, so you got to go through the root like these. And here's minus to order 2, so therefore I look like a little parabola like that. Okay, so to order 2 on other side. And the middle one's odd order, is a straight line. If it's 3, then it has a little S shape. But it's a straight line. And then I play connected dots. And basically it goes like this, it goes like this, it goes, and keep going downwards. Remember those two on outside, minus and plus. Okay. So, and this is the finished product. It turns out if you plot it, look at close enough and adjust the ratio, it looks like that. Okay, so it's fairly accurate, in other words. Okay. Now, this is local, what is in the middle, okay? The picture we got. And that, of course, is in the little middle pieces. If I keep zooming out in space, basically I see x to the fifth power because this is the minus fifth power because this is the minus 50 equation. If I multiply out, the globally is minus x to the fifth power. That's why it looks like that. That little twist. Okay. So that's it. Okay, and bye bye. Okay, and do the homework and have a good day. Bye bye. Bye bye.